were discussing last time. So last time we talked about influence, um, leverage and influence, and the key was this. Basically, if you want to remember a single idea, which is very influential itself, is like this leave one out identity or leave one out idea. So if you want to measure how much influence a data point has on your fit or on your model, you can leave it out and fit the model or refit the model and then compare with the original model. So what you can do, for example, is you can look at this difference in the beta hat. If you're doing a linear model, everything follows from the beta hat. And so we did a little calculation, which I did it halfway through, and then the rest assigned as a homework problem. So you can go through and verify this formula. From this, you get this so-called press residual or leave one out residual. So you're comparing yi to the prediction of yi based on a model that does not see the ith data point. Okay, so this has a strong, let's say, prediction right. So you're predicting something that you haven't seen, as opposed to the case where you're predicting based on, like predicting y based on the model that also has seen yi. So it's quite different, as we'll also go over this in this lecture in a different context. So in this case, it has a closed form, so you don't need to evaluate this. And if you look at these, we'll see, I mentioned this, these you can assemble into something called press residual, basically. You square them and sum them, it's like an SSE, but with these leave one out residuals, and this is called prediction error or prediction, not sure what R is. Is it a regression or prediction? I forgot. Error sum of squares. So this could be like, so this is called press residuals because they form this press statistic. And we'll revisit that. In any case, so this can be computed without the need for refitting the model. So in the linear model, you don't have to refit the model again. And so what will happen is you would do, so there's some ways to try to summarize this information. So one thing that we people liked a lot, traditionally, this quick distance tries to capture the deviation in beta hat minus beta hat I in a single number. And you can see there are two factors we discussed. There's this residual outlierness, and then there's the leverage outlierness. So it measures the outlierness in y direction and x direction, and together they kind of tell you how much influence you have. This naturally comes out of this measure, so you don't have to do a heuristic argument. This measure itself also has some sort of a meaning, as we discussed. So this properly normalized so that it doesn't depend on your problem. It's normalized on the S scale because of this little fact here that you can prove. Anyways, so I don't want to talk too much about it. We already talked about that. And then we also went over this idea that you can basically generalize to modern machine learning. So in machine learning, let's say deep learning, if you've heard about it, people train these highly nonlinear models. So now you have this phi, which is your prediction. So this is trying to predict, predict y star. And so it's a complicated model. It's like a neural network, has many parameters. So the parameters are like these thetas, and it has an input, x star, and then you get an output. For every parameter, you have a prediction. What you do is I believe I mentioned this last time. Yeah, so you go and oftentimes fit them using a so-called empirical risk minimization. So this is basically you define a loss function. It could be the least squares loss, or the squared error loss. So if you have the training data points, you measure the distance of your prediction on the ith xi, or jxi to its y, let's say if it's a regression. So this is the prediction of yj, so you try to minimize. This is really the least squares loss. If phi was a linear model, this would be, so this would be phi theta xj would be, or x would be really theta transpose x in linear models. But you can have a very complicated neural network that's doing the job and then try to minimize this. And you can think of this as the loss of the jth data point, and then you average them, you try to minimize this average. So you have like a theta hat, which is the argmin of this loss function. And this thing basically. And once you have it, then you have a predictor. So this guy is now your model, so phi of theta hat x star, and it predicts a new data point, the y of a new data point. And one thing that you can ask, similar to our case in regression, is what data points are the most influential? So how much influence each training data point? Now, they're kind of training points rather than maybe traditionally like sample or observations. In statistics, in machine learning, they're also like oftentimes training data. So which of the training data or which of the training points are most responsible for a particular prediction? And then what you can do is you can look at this leave one out effect on theta. So you remove one data point and see how far the theta hat moves. And then you can do it in a brute force fashion. So you can just leave one of the data points out and retrain the whole model. But that's very inefficient, especially if you have like millions of data points or trillions of data points. And then the model is like 100 million parameters. This is going to be very costly for a single data point. So people try to approximate it. If you do a little Taylor expansion, this is not very difficult to show. You basically Taylor expand the loss around the theta hat, and then you would show that this is approximately, if you do a second order expansion, you would get this result that there's this Hessian inverse at the theta hat multiplied by the gradient of the loss or on that data point. Okay, so this you can compute easily without refitting the model. It has the same flavor as our kind of closed form leave one out formula. And moreover, if you have, if you look at phi hat x star minus phi hat I x star, so this is how much the prediction changes for that particular data point. You could do like a little Taylor expansion again. So this is like gradient of phi. If you do a first order Taylor expansion, it would be like gradient of phi hat, theta hat x star transpose times theta hat minus theta hat I, right? And then you have this formula from above, and you plug it into this, and you get this result, okay? This is maybe missing 1 over n here. But you just multiply by this gradient. And this tells you basically how much the prediction varies. Okay, and you can call it maybe the influence of point I on your prediction. And based on this measure, you can like rank the training data points, and this gives you a way to do kind of a interpretation or attribution. So if you want to see, for example, you train the class, so this is mostly for regression, but you can also like change the loss to logistic loss or cross entropy. You do like classification. You had like, for example, a neural network, deep model, you trained it. Now you give it this image and it outputs like cat. So you want to see why it thinks it is a cat. And if you compute these scores and then you rank the training data, you come up with, okay, maybe these 5 images are explaining why the model thinks this is a cat, because it's like relying on, and these are the most influential for that prediction. And it gives you a way to kind of interpret these black box models in a sense. So that's what this idea in this paper, highly cited paper from 2017, tried to bring back these statistical ideas to machine learning, and was hugely popular. And then there are like subsequent work, which you're welcome to see. People try to extend this to different other models like LLMs or other things that I'll let you try to dig into if you're interested. Okay, so this is like a connection to modern machine learning from classical statistics. Any questions about this? So there's a bit of non-linearity here, but you do linearization and Taylor expansion, and then you could do kind of, and then the issue is that even that formula is not easy to calculate, even though this like, and then I encourage you to go calculate this for the linear regression. It's not going to be exactly, this is not correct. It's not going to reduce exactly to leave one out identity. There's like something missing. Yeah. Yes. The Hessian is the main one because it's like a, it's like a matrix. So if the parameter is like p-dimensional, this is going to be p by p. So if you have a million, 100 million, or let's say if you have an LLM, which is like a billion parameters, it would be a billion by a billion parameter matrix. So people try to approximate this even. So even this is not viable. So there are a lot going on. I mean, I think if I don't recall, but there's the bulk of this paper trying to approximate that quantity rather efficiently. Any other questions? Okay, and then there's a bit of other stuff that's related here. So very quickly, I'm going to mention this. So another area of modern, let's say, machine learning or statistical kind of application where these traditional ideas, let's say, especially the leverage, comes into play is this idea that you want to do approximate linear algebra or approximate OLS. So if you remember, we had like the estimate, which is like beta hat is X transpose X inverse X transpose Y. We have been writing this quite often. It's like good for theoretical analysis, but in practice, that's not how you compute the beta hat. You try to solve this linear system directly. And there are like many different ways of doing it efficiently. You don't necessarily try to invert the matrix. You just want to solve this linear system. This is a matrix, this is a vector, and it's like a positive semi-definite matrix. So it has like, there are good ways of doing it, but even good ways are going to be costly if your like data matrix has a billion rows, for example. Okay, so you try to approximate in those cases, it may not even fit in memory. So what you can do is you can try to sample some of the rows. This is like a trend in machine learning, or like it's called approximate linear algebra if you want. So for example, want to compute the eigenvalues of a matrix or solve a linear system, but the matrices involved are too big to even fit in the memory. So you try to do approximation, like a stochastic approximation. One way is to sample. We can sample the rows. This is called sketching. So it's like an artist goes like just sketches a bunch of lines, doesn't like fully draw the thing. So you sample some of the rows and throw away the rest. As you can see, like the columns are the same. Okay, so some of the data points you can remove. Okay, you lose some information, but the idea is that you don't need to necessarily naively uniformly sample. You can be more clever. We know that some in the data points are more influential, right? So you can try to keep those more often. And so that leads to this idea of leverage score sampling. So you can sample, so these are the leverage scores. So these rows will have more influence, like the ones that have higher HII would have more influence in the total fit. So you try to include those more often. So if you define like a probability distribution under like the index of the rows, HII divided by the sum, we know that the sum is p plus 1. So you get this very simple probability distribution. You can sample the rows with these probabilities. And then you have to also adjust a little bit by rescaling. I don't know if this is correct, but you can check. I'll try to post some sort of notes with more details. And then we can show, for example, these type of results that if M is of the order of P, P is going to be this dimension here, times, let's say, epsilon to the -2. Epsilon is your accuracy budget. Okay, then the beta tilde that you get out of solving this sketch regression will have the same kind of least squares cost, up to a factor 1 plus epsilon of the global, or the one that you fit on all the data, okay? So you can get up to a factor of like 1 plus epsilon of the cost of the true regression, SSE of the regression and all, okay? So this is also nice because this uses the ideas. There are other ways of sampling, of course, but and this says optimal. Optimal is not necessarily correct. This is a good way of sampling or sketching. So this idea is called a sketching, yes. Not sure I understand the question. So yeah, so you throw away the x's and also the corresponding y's. So there's like the y's. You pick some of the rows, and you delete them basically. Or just let's say we pick, let's say I keep these rows and keeps these data points, like the corresponding y's, and now I fit. So I subsample basically, sample some of the rows, and then I just fit a regression to this new data point, the training set. And the idea is that I would not lose much. So this is going to be bigger. So this is going to be on the other side. This is going to be always bigger than y minus x beta hat. Because this has more rows, the ability to, you can reduce the loss. But on the upper, like how large this is, you can control. It's not going to be far off. So we within a factor of 1 plus epsilon. Okay. And if you want to be very close, then you can see it blows up. But if you're okay to be like within a factor of like, I don't know, 0.1 or whatever, this is going to be manageable. Okay. So this idea is very useful, especially let's say if you do kernel methods, which are, I don't know if we will not have time to discuss, but that's another case where it's hard to implement a kernel ridge regression, for example, and the people do a sketching. The other thing that we can do here is, and it's also not correct, I like remove this, but just briefly mention that if you go back to the like a conformal prediction, what we did was we trained the model on like a part of the data and then try to calibrate on some other part, right? So you use like split your data into two parts and try to calibrate. Basically, the calibration was like you try to predict the calibration set, and then based on the size of the residuals, you set the threshold for the confidence interval. That would lose some statistical power. So you're not using all your samples to fit your model. So you're like reserving like a big chunk for calibration. One question is that can we like do better? Can we like maybe use all our information, like all samples in training and maybe also calibration? There's this jackknife idea or jackknife plus here that tries to do that based on these residuals. Kind of, if you remember, these residuals have the same idea, like you train on everything but this ith data point and then try to predict it. It's as if you're calibrating on this data point, but I can move it around and I can compute all of them. And if you gather all, basically we have trained on all data and I've calibrated on all data as well. So these have this information, and somehow if I manage to combine these into something that gives me like a conformal prediction interval, then I'd expect to have a much better, like maybe lower, like a smaller interval. Okay, so the details I'll try to fix maybe in a set of notes and send you, but this is the paper. It's a very recent paper. I encourage you, if you're interested, to have a look. It should be readable, given that now you know what's the conformal prediction, and you get like a result like this. You pay an extra factor of 2 here. But you can construct like a conformal prediction interval based on these press residuals or leave one out idea. Traditional leave one out is also like leads to this jackknife. It's a form of bootstrap. This is called jackknife plus because it does a little bit more than that. Anyways, okay, so this is like a wrap up of this section. So we talked about these leverage and influence, and then connected it to some modern applications like training data attribution or influence, they're like a jackknife plus conformal. There's also this idea of differential privacy, which I'm not going to go into, but this is a huge literature on itself. And it has the same flavor in the sense that if you think of privacy, so if you fit a model like a linear regression, and based on the coefficients, I can recover the training data that's not going to be private. Okay, so if you fit a model like a deep neural network and I can extract the training data out of the model, then it may not be private. It would be good if I have a model that does not rely on any single data point so much that I can extract that data point. And this goes back to this idea of like influence. So if a point is very influential on your fit, potentially you can invert it back and recover the point in a sense. So this differential privacy idea is very similar, but it asks for a more a stronger notion. So if you remove one of your data points and replace it with something arbitrary, you don't want the fit to change too much. Okay, so it's like more of a, rather than leave one out, it's like replace one out. You replace one out, and over all possible data points in a range, you don't want the model to change too much. And if you can guarantee that, then you have some sort of differential privacy. This is a notion of differential privacy. I'm not going to go into, but if you're interested, this is a good like off-ramp to like dive into that literature. Okay, and this is the press residuals, and I'm going to start the next topic with this. Any questions about influence? Okay, this is lecture 16. It's supposed to be current lecture, which is just starting off. Questions so far? Okay, so today we're going to talk about another exciting topic, which is maybe the most exciting topic for statisticians, or you can like think of it as a central question of statistics is which model should we pick? Okay, so if you have a collection of models, what is a good model, or which model should we pick? So which model should we pick? Requires you to define what is a good model. Okay, and so far we have had like a set of predictors, and you had a linear model. You assume this is a good model, and then we went about business. But let's say if I have a pool of predictors, and I maybe know that not all of them are predictive, I want to select a subset that's predictive. That is an example of the so-called model selection. So what we're talking about is model selection. I'll tell you about the first piece, but the task is this. So I have a candidate collection of models, which we, in this case, think of as subsets. So what we really have is, let's say, I have the indicator, which is the intercept, and then I have a collection, and we call them Z1 up to ZQ. These are, let's say, centered covariates. You can call them X1 and up to XQ if you want. So there's a homework problem that tries to convince you that centering doesn't change things much and it's cleaner. So centering basically removes the residual against this column. And so, okay, so I have these centered predictors. I have Q of them. Okay, Q, which is often much larger than what I want to keep in the model. And the task is to pick a subset S out of this 1 up to Q, and then include only those predictors in the model and then fit a linear model with those. Okay, so for each subset S, I'm going to have a linear model, which you can think of it as like XS. This is the, let's say this is, maybe we can have like an X. This is capital X potentially. And XS is just picks the columns that are in subset S. And then times some theta plus epsilon. So this is going to be my model if I select subset S. And for each subset S, I get a different model. So you can think of it as a model. It's identified with a subset in our case because we're going to look at a linear model. In general, you could have like multiple different classes of models. and then in each you can have multiple subsets of variables. But our task here would be to select a subset of these covariates, hence identify a linear model, where the design would have those predictors only. Okay? So I'm going to use the ds for the number of, so ds is the number of parameters, like free parameters of the model. So this notation, this is the cardinality of a set. Okay, how many elements S has, and then I have another like extra here, an extra free parameter for the intercept. Okay, so you get cardinality S plus 1 is the total number. So we used to call this P. You can call it P if you want, but I'm writing it this way so that you can see it depends on the size of S. Okay. So the question is that among which one do we choose? Okay. And then there are two goals. One is one goal could be like to predict well, choose the model that predicts the best. Okay, this is very general, and this is going to be the bulk of the lecture, is going to focus on trying to define a prediction criteria or prediction error that then allows me to pick a model based on it. The other criteria is to recover the true subset S star. So if there is a true subset, if there is a true model, let's say there exists a true model, slash S star, such that Y is X S star theta plus epsilon, then I would like to be able to recover this S star. This is called subset recovery or like support recovery or something like that. And this is generally harder, much harder. And it requires you to assume that there exists such a model actually. The prediction criteria does not in general require you to have actually a linear model. You can come up with a more general model where you assume that Y is really just, so this is needed for subset recovery, what they call support. Support is support of the parameter, but or consistency, sometimes called model selection consistency. Consistently recovered. Okay. Let's call this model selection consistency. Consistency means like you recover the true model. This is better, more general. So you need some model like this for prediction. We'll see that for prediction alone, it is enough to have just Y is mu plus epsilon, where epsilon is like maybe normal 0 sigma squared I, or satisfies actually E1 even. Okay, there's a mu vector here, but I'm not going to assume a structure like a linear structure like this necessarily. And it's much more general. Okay, and so if the task is to predict well, this is an interesting criteria. Okay, so the criteria that we saw, so each one is trying to measure how well we predict the ith data point, given that I haven't seen it. And when I sum them up, this is like an SSE, but it's actually a good measure of prediction error. So I can use this actually, which we call press. It's equivalent to leave one out cross validation, and you can use it as a model selection criteria. So you can choose the model that minimizes this quantity. Okay. I'm going to work towards that, but we already have one criteria. If prediction is our task, this gives you a good criteria. But I'm going to explore this idea a little bit more, so you can have a much better like theoretical understanding of what is going on. The first thing to note is that the sorry, I think this is maybe, let me switch to okay, switch to this. These are from the morning session. Switch. Do I have actually the updated version? Yeah, okay, so let's do this. Yeah, so what we want to do is first note, which we have already noted that like the SSE is not a good measure, for example. Okay, so SSE is measuring 1 over n summation I from 1 to n, let's say yi minus mu hat I. This was not good. Anyone remembers why this is not a good model selection criteria? I say if prediction is my goal, this is not good. Unfortunately, it says on the slides why it's not good. But... So the problem is this is gonna always go up if you keep adding predictors. Sorry, it goes down. So this SSE goes down or R squared goes up. Okay. And you can get a perfect fit, so you can drive this to 0. You can drive to 0. This is what you can call training error. Okay, so this is the prediction of point I uh, given that the model is trained on the same data. And so this is possible. I mean, it's possible to drive this to 0. And in fact, you can prove by like the projection idea. If you add a predictor, you enlarge the image. And so the projection error would be smaller always. Not smaller, but at least it's not going to be bigger. It's going to be less than or equal to. So SSE of M would be less than or equal to SSE of M prime if M is a subset of M prime. If one model is included in the other, which means that the subset of predictors is included in the other, then the SSE is going to be like non-decreasing. Sorry, the other way around. This is for the, so SSE would be larger or equal. The R squared would be, so the smaller, the larger the model, the smaller the SSE gets. So as if you use it as a model selection criteria, you always pick the largest model. You always are going to include all the Q variables that I mentioned. Okay, so this is not good. And by the end of this lecture, hopefully you have a better understanding of what is wrong with this. Okay. So what we really want is a small error on a new data that we haven't seen. Okay. If I manage to get a prediction error on new data and I drive that to 0, that would be really ideal. Okay, so any future data point I can predict 100%. So that's what we want to do. So, and you'll see that the training data, the training error, and then this other thing is called the test error as well. So prediction error or test error, they always part ways at some point. Then you try to add predictors. Okay, so to get a sense of theoretically what's going on, so fix a query point, x star, and this is going to be fixed in the sense that it's not random, and then draw a fresh sample, yi star, as mu of x star plus epsilon star. So epsilon would be independent of the training data. And the variance is going to be sigma squared, the same as the training data. Okay, and then my prediction on this new data point would be mu hat of x star, which is x star transpose beta hat. Okay. So for the next result, we actually don't need even the linearity. So what I'm going to look at is the expectation of y star minus mu hat x star squared. That's the prediction error on the test data. And then I'm going to take an expectation under the randomness in both the test data and the training data. This is really kind of an ensemble quantity. It averages out over all training and all tests. You can try to condition on the training data that you observe and just average over the test data, but here I'm doing both. It's worth at some point thinking about what it means. But if I do this, there's a very simple like little argument that you can do. We're just replacing it with, this is mu of x star, the true mean function plus epsilon star from this assumption. And then if you expand, you just basically consider these two terms together. And this is another term. If you expand, you get this difference squared, and you also get the expectation of epsilon squared, and then you get the cross term, and the cross term goes away because of the independence between the training data and the test data. I encourage you to write it down. It's very simple. So this term, the first term, is like an irreducible noise. So this is like the noise floor of the problem, or this is what we can improve. No method can like drive the test data, like test error to zero. You can see it here, unless there's no noise. So if there is a noise in the problem, this is the best that you can do. I mean, this could be zero, but this can't be zero. This is very different than the training error, which can be driven down to zero. And this part is what really the models can work with. And you can think of it as the MSE, mean squared error, between the true regression function, and the estimated regression function. Okay, and as we'll see, this has this interesting decomposition into a bias squared plus a variance term. Okay, so the punchline here is that I can focus on this part of the prediction error. Okay, this part I can't do anything about. Okay, so I can alternatively try to approximate this quantity and use it as a criteria or criterion for model selection. Does this identity make sense? Just expand for yourself, and then you'd see the cross term goes away because the test error is independent of the training error. So far, so good. Okay, so the next thing is I'm gonna, rather than look at this is a little bit tricky, but I'm gonna hope that you understand what is going on here. So instead of looking at it over a single x star, I can average this over the training xi's. And this is okay for various reasons. I'm gonna look at this quantity. Okay, sorry. Because technically we want to, what really happens is that we want to also take the expectation over x star, because we don't know a particular point. We want to say, take another expectation under x star as well. Here as well, so far it's fixed. Then it would be just a quantity that doesn't depend on anything. Yes? What part of the slides are we talking about? This? Oh, this is parentheses. Is that? Yeah. This is, no, let me write it properly. This is mu of xi minus mu hat of xi. Yeah, I should write it a little bit clearer. Okay, that's kind of the idea. I'm gonna, instead of looking at a fixed data point, I just wanna like have it for average of all the data points. And I'm gonna do it over the training data. This average is gonna be approximately similar to like a generic data point. This you can like argue with me that, okay, so you're back to doing it on the training data rather than test data, but the issue is that issue that we had is not gonna appear here because this is like measuring the distance of mu hat to the actual mu, which we don't observe, rather than yi. So if it was yi, this would be a problem. So if I measured actually this wouldn't be a problem because there's an expectation here. So for two reasons. So it's like, this is bad. Mu hat xi. If I take the expectation, it would be okay. If I take the expectation, it would be similar to this. Or if I manage to even look at this quantity, I mean, this would be okay. If I look at this guy, it would be okay. Even without the expectation, if I look at this quantity and try to minimize it, because I'm trying to say that mu hat is close to the actual mu. And if I can drive this to zero, it means that I am interpolating basically mu on the training data, and if mu is like continuous or like well-behaved, it's gonna like behave well in the middle. The issue is that I don't know mu I, or I mean the actual. But anyway, so this makes sense. Any like complaints, or we are computing this quantity in sample on the training x cells. but that's fine. So this is kind of like, the best way I can say this is like approximately like expectation over x star. This is by the law of large numbers kind of thing. This is, you can think of it as just some sort of a function of xi, and it would converge to, by the law of large numbers, converge to the expectation of f of x star under x star. So this would be like expectation of x star, and then expectation of mu of xi. Sorry, mu of x star minus mu hat of x star. So the first expectation is on the randomness in everything else except x star. So far we have fixed it. And then if you take another expectation out, this averages over all possible test data. And so this is a good measure. This is going to be by kind of law of large numbers in a sense. It's more tricky, but anyways, that's my attempt to justify that you can look at this quantity averaged out over the training xi's. Okay, so we're going to fix this. And so what I'm going to get is I can look at either this, the average, or I can just look at this part. This part, if you look at it, it's just the expectation of summation I from 1 to n, mu of xi minus mu hat of xi squared. And this is really, this is mu I. This is mu hat I. So what I really have is the expectation of the norm of mu minus mu hat. Okay, that's the kind of, the mean function evaluated at the data points gives me a vector. Mu hat evaluated at the training data point gives me that fitted vector fitted values that we have seen. So I'm looking at the expectation at the difference of these two vectors. And I'm going to put an S here to emphasize that this depends on the subset or the model. Okay, so in the end, what we arrive is at this measure. Okay, which I'm calling the risk, fixed design risk. Have people heard about the risk in 100B? It's a decision theoretic kind of term. So if you take one like 200B or like a serious course in theoretical statistics, they start from decision theory. You have loss functions and you have risk. Risk is the expected loss. This you can think of it as a form of a loss, and this is the expected loss. So the whole like point is that let's call this the risk, even if you don't. Yes. It can come back. So the thing is, I'm going to minimize this over S, so it doesn't matter whether it's 1 over n or multiplied by n, okay? So I'm defining it like this. If you want, you can define the MSE. You can call the MSE of S to be the 1 over n, the risk. Okay, so this is really going to be that. So if I do 1 over n here, okay. So let's call that MSE of S. Let's call this the risk. The issue is because we're going to minimize it over S. We care about this as a function of S. A constant factor or a constant addition of a constant, addition of a constant or multiplication by a constant doesn't change things, okay? Right. So we could have started from this quantity. So this is like, it's gonna, if you define it like 1 over n here, it's gonna get multiplied. So all these values get multiplied by 1 over n. Right, so let's say you have like values, for example, like 10, 15, maybe 5, 9. And then you can, if I divide it by 100. So it doesn't change which model minimizes it, okay? So the one that minimizes it is this, the one that minimizes this is that, right? If you multiply or divide, or even if you add a constant, doesn't change the location of the minimum, okay? Change the minimizer, change the minimum value, but not the minimizer. We care about the minimizer, okay? Sounds good? Okay, so I spent a lot of time arguing that this is good. Now let's calculate it. So can I maybe, not sure how to create a new. add a page. Good. So let's do it here. I'm gonna maybe cut, move this here. Okay. Now let's calculate this quantity. So I know that mu hat S is, calculate R mu of S. What is mu hat S? I'm going to help you. It's just h of S times y. Okay. Remember, like it's a projection matrix of the model, which I'm writing it as this because it depends on the predictors, times y. So if I look at the mu minus mu hat S, that's the quantity we have to look at. I get mu minus hs times y, but y is really mu plus epsilon. Okay. So what I get is mu, or like I minus h s times mu minus hs epsilon. Okay. So this is just replacing what we know about y. Okay, so the risk now is R mu of S is the expectation of this quantity squared. So it will be the expectation of this whole thing squared, the norm squared, right? So when I square it, I get three terms. So I get I minus hs mu norm of this squared, and this comes out of the expectation because it's constant, plus the expectation of the second term. We can drop this sign, so it will be expectation of the norm of hs epsilon squared, and then I get the negative this is going to be, I'm going to write it here, negative 2 times the expectation of I minus hs mu transpose times hs epsilon. Okay. What a complicated term, but just the transpose of this times the transpose of that. That's like the cross term. Okay, so questions? So what happens to the cross term in any reasonable statistical course? 0, yes. Until it's not, but you get a lot of mileage out of that statement until you hit the wall. Why is it 0? So this is a linear, like this whole matrix is a linear operator. So I can move the expectation past, right? So the expectation can be moved past this, applied to the epsilon directly. And the expectation of epsilon is 0. So I encourage you to go through, you should be able to really easily argue this for yourself. Okay, so I'm left with this term, which is going to be there, and then this term. So let's calculate this term. How do we calculate this?
Epsilon transpose Hs epsilon.
Yes, so you get epsilon transpose, let's say Hs transpose Hs. So you transpose of this would be that, and then this, but then this is Hs, right? Because Hs is an idempotent symmetric matrix, so we get expectation of epsilon transpose Hs epsilon. What is next? How do I deal with this?
Expectation is can also be linearly operating on one point epsilon. Transpose of epsilon. So
it can do, but this is a problem because they're on both sides. It's not like they're collected on one side. So I can't like pull it. There's a trick here. There are different ways to deal with this. Someone in let's see what you guys think. So how do we deal with this? It's not like the case where I had, remember there's like the expectation of A, B, C. If B is the only random thing and these are constant, I can move it inside. But if these two are random, this is like constant, doesn't go in, right? So it's like a problem here. But there's an easy fix in this case. So let's see how you guys think we can deal with this. Maybe think a little bit. Yes. Yes, okay. Someone else mentioned this in the first. So that's a very nice way of dealing with this. Once you have like a symmetric matrix and you run out of options, you do eigenvalue decomposition. In this case, we know a lot about the eigenvalue decomposition of this, right? So what do we know about this? It's U, the eigenvalues are 1 or 0, so this goes like this. And if you plug in, this is really a quadratic form. If you go back to how we dealt with the quadratic form, trying to prove the chi-squared, we did the same idea, right? So this U transpose epsilon end up having the same distribution because this is a rotation, or like an orthogonal transformation, it has the same distribution, so you end up having like, let's call this Z. You'd have Z transpose something like this, Z. And then what will happen here? You'd get basically Zi squared, I from 1 to how many ones you have? How many ones do you have? Will be the rank of the HS, or the dimension of the image. Well, remember? DS is what you had, like the notation. So you get the expectation, and each one is, let's say, you don't even have to assume Gaussianity here. That is gonna leave the covariance invariant. So if the covariance epsilon is sigma squared I, the covariance of Z would be sigma squared I as well. So these will have sigma squared variances. So this would give you sigma squared times DS. Okay, that's one way of dealing with this, which is a very beautiful way. And there's another way. Have anyone heard about the trace trick? Yes. Diagonal matrix. So we don't have a diagonal matrix here. So what is the trace trick? The trace trick is like this is a scalar. A scalar, you can think of it as a 1x1 matrix. I can write it as the trace of itself. Okay, the 1x1 matrix has a single diagonal element and traces the sum of the diagonals. So this is the same as the trace. So why do I want to write it as a trace? What properties do traces have? Yes? Yes, yes, so exactly. So they're cyclically invariant. So I can write it as, I can move them around cyclically. So basically I can move, for example, this to the other side. And it doesn't change the trace, okay? Why do I want to do that? Because now I have the random part like close together. Now I can apply my linearity idea, right? So expectation moves past the trace. Trace is linear. Also moves past this, which is a linear map. So you get the trace of HS, expectation of this quantity. Okay, and this is sigma squared I. So I get sigma squared trace of HS. And trace of HS is, this like the sum of the eigenvalues as well, or rank of it. Anyway, so this is the projection matrix trace is DS. Is another way of dealing with it, okay? This is more general because you don't need to know the eigenvalue decomposition, you just need to know the trace of the matrix. So cyclic property. Allows me to pull the random parts together so that I can apply my nice lemma. Sounds good? So if you go back and like plug it in, so we have this and we have that, you'd see that we proved this result. So this risk is this quantity plus that, and this turns out to be really the bias. You can easily show, another way of dealing with this was to add and subtract. I could have added and subtracted expectation of mu hat S, subtract and add. And so mu minus the expectation of mu hat S is the bias, and this turns out to be this term. And then expectation of mu hat S minus itself is squared is the variance, and so this is the variance there. So the risk, like this is kind of the squared, a quadratic risk basically decomposes into the bias, or you can think of it as lack of fit, and the variance. Okay, and the thing is, you can see this variance is going to grow as you add more predictors. Okay, let's go to this slide. So this kind of summarizes everything about the nature of the problem. So as you keep adding predictors, generally you would reduce this bias. It could stay the same or you could reduce it, but this keeps going up, and then there's going to be a sweet spot. Okay, at some point, what happens is that this bias, you can drive it to zero, and that's where the model is so-called adequate. So if mu turns out to be inside the image of xs, so you add enough predictors such that the image spans like a subspace that contains mu, then when this is projecting, basically this is equivalent to like mu minus hs mu. Okay, so mu would be equal to hs mu because when you project it, it's not going to change. So the bias will go away. So models on which the image of x is, or for which the image of x contains mu, will not have the bias. But at that point, if you keep increasing, like adding more predictors, this is zero, this part is going up, so there's no point in doing that. Okay, so it could happen that even for models that have non-zero bias, it's no point in trying to add more predictors because it could be that I reduce the bias by a tiny amount, but increase the variance a lot. So if the sigma is very much, very large, it could be that adding one predictor, which adds sigma squared, is not going to be offset by the drop in the bias. Okay. So this is kind of the bias variance trade-off, or the fundamental trade-off in model selection. Does that make sense to people? Right. So this would be very good if I could compute this measure. I could just apply different S or test it and like score different models and then pick the one that minimizes. So there's a problem with this though. We can't apply this in practice. Why we can't apply it in practice? Yes, but that is easy to fix. I can try to estimate it. There's a bigger problem. What is the problem? We don't know the other term. We don't know mu, so we don't know the bias. If I knew the bias, basically I could have done it. So what we're going to do is we're going to come up with criteria to try to estimate this quantity directly. So you're going to estimate the risk. You're going to basically have unbiased estimators of the risk that then we can use to do. So, but this criteria, bias plus sigma squared ds, you can think of it as the oracle. Oracle risk, or if an oracle mu, like an oracle that mu is mu, could compute this oracle subset or oracle model. And we are going to try to approximate this oracle behavior. So one way to try to do that is going back to the idea that we had the training error. Maybe I can use the SSE to try to approximate this. But what happens is, as we already saw, but this picture also captures it much more nicely, this is bias low. So this underestimates this risk or the prediction error. And if you try to plot the SSE, which is the training error, or SSE basically divided by n, the MSE basically is the training error, versus the test error, you'd see that they come down, and at some point they start to diverge. The test error goes up while the training error goes down. And this gap, I mean, people have called this the optimism. Okay, so the training error is optimistic about your test error. And if you manage to estimate this gap, which we can call the optimism, if you manage to estimate the optimism, I can add it to the training error, and I get a good estimate of the test error. Okay, that's one way of dealing with this. There are other ways, so I'm going to go over them quickly. So let's do the optimism route. So this is the training error. Now I'm replacing mu hat I with y hat I, which is common. And then this is what some people propose to look at, which is very close to the prediction error. So this like in-sample prediction error. What I'm going to do is that instead of yi, which is used in the training, I'm going to sample a fresh yi prime at the exact same xi. So yi prime would be mu of xi plus epsilon I. It's very similar to the test data point that we got, but at the particular xi, because now we're like looking at the in-sample xi's. So this is going to be, if you look at the expectation of this, this average is very close to the prediction error, or actually it's a prediction error on average. We can call it in-sample prediction error. So I'm going to measure the difference between the two and call that the optimism. Okay, it's going to be exactly the quantity that we were looking at, in fact. So this is going to be exactly the risk divided by n. This I believe you can show this is R mu S divided by n. Prove it for yourself. Yes. So you had a training data xi, yi. So if you use the yi here, compared with mu hat I, that would give you the training error. If I use the same y hat I, but assume that I can draw another sample with the same xi, but a new yi. So there's stochasticity in the model, right? Just draw another sample. Okay, another observation.
So you have data drawing another sample of where I is given the same size.
Given the same xi, I draw another sample from the model, yes.
Okay.
Yes, yeah. So it's going to be different than yi. It's going to be random, and it's going to be independent of the training. That's the point. This is going to be independent of the training data. And I believe you can show that this is actually equal to the quantity that we looked at. The thing is that it's very similar to this behavior. Here, I started with xi and a new yi. But if I have xi here, the equivalent thing would be yi prime, because I need to sample a new data point. It's not going to be yi. So this would give you the same behavior. I could have written it a little bit better, but this quantity is really the quantity that we were looking at divided by n. So the difference between the two is called the optimism, like in-sample prediction error minus training error. And then there's this nice result that the expected optimism, the expectation here is over the randomness of the training data. This is going to be 2 over n summation I from 1 to n covariance of y hat I and yi. Okay, I'm not going to prove this, and you're welcome to prove it. Very easy to prove. You just expand the two sides and then subtract, and then you notice by independence some good things happen. This result is very general. It doesn't require you to have mu hat I, which is a linear model. It could work for nonlinear models as well. Once you write down the proof, you'd see. And so if I manage to prove it for yourself. If I manage to calculate this quantity, then I get an average notion of optimism. I can add it to the training data. Sorry, training loss, and then I get a good criteria. So let's calculate this for the OLS. So if you look at the covariance of mu hat is really y hat again. So I'm interchangeably using this. Some people use y hat. I use mu hat. So we're calculating the covariance of mu hat I as well. So we're calculating covariance of mu hat and y. This is h, let's say s, y. And so I get hs times covariance of y. This is sigma squared I. I get sigma squared hs. Okay. So what we get is if you look at the sum here is really the trace of that cross covariance matrix. So you get the sigma squared trace of h, which is sigma squared ds. You already seen this. So this is a measure of, so this for linear models would be 2 over n sigma squared ds. Okay, so what it's saying is that if I look at the optimism corrected penalty or like a criterion, this would give me the training error. I should add, because this is the difference between the quantity that we want and the training error, so I should add this quantity to it, 2 over n sigma squared ds. So this would be MSE. Sorry, this would be SSE. This is really SSE divided by n plus 2 to the n 2 sigma squared ds. Okay. So now this is a quantity that I can calculate easily, assuming that I know sigma squared, but I can estimate sigma squared. And then I can minimize over s. Okay. Does that make sense? You just have to argue for yourself that this is true. What happens is if I take the expectation of this would be the correct quantity. Okay. I could do this, or I could like multiply by n as we have seen. That doesn't matter. I could, sorry, there's an extra 2 here. This should be, yeah, 1, 2. Would be 2 over n. I can multiply by n and you get, I can also look at this. This is another viable quantity. Or you could also look, we'll see. I could look at something like this. I can divide by sigma squared. I get, this is also another like equivalent. These are all equivalent criteria to try to minimize over s. Okay. The key is this correction that you can see this is going to always go down as you add samples, but this is going to go up because the diamond, this is like a complexity measure. So it measures how many parameters you have, and it's going to go up, and there's going to be a trade-off. Okay, and the expectation of this would be exactly the thing that we were trying to compute. Okay. I'm going to drive this another way shortly, hopefully. But before doing that, I just want to point out that if you look at this quantity, you can see in linear regression, this turns out to be sigma squared ds. So if I divide by sigma squared, this gives me ds, which is the number of free parameters, or the degrees of freedom of the model. So for that reason, people have defined this quantity, 1 over sigma squared summation covariance y hat I and yi as a notion of a degrees of freedom for a general, even nonlinear estimator. So if I define this quantity to be df, and it turns out happens to be equal to this quantity as well, which I'm not going to prove. This is due to a Stein. This is for under Gaussianity, under a Gaussian model. So y hat is in general is a nonlinear or linear function. So y hat in our model is like HSY. But in general, it could be a nonlinear model. And this quantity actually ends up being the partial derivative of y hat I divided by partial of yi, which we've seen. This is like the leverage of scores in linear models. So it gives you back the trace of h. But in general, this allows you to calculate this degrees of freedom. The thing is that the optimism, you can write it as, if you go back up, if I divide by, multiply by sigma squared, divide by sigma squared. This I called degrees of freedom. So the optimism is 2 sigma squared over n times the degrees of freedom of the model. What does it mean? The degrees of freedom, it just means exactly that. It reduces to the notion of free parameters or dimension in the linear model. So for that reason, people think of this as a generalized notion of degrees of freedom. So the optimism is this. This is the only thing that like really requires some proof, but I'm not going to go there. So just know that there is a more to this story. You can do it for more general models. But okay, so this is the expectation of the optimism is this quantity. This is the optimism theorem due to Efron. And so if I add back this to the SSE, I get. You can think of it as basically this is 2 times the degrees of freedom. This is in the regression. This is like, in general, we get this plus 2 times the degrees of freedom. There's a more general formula. Okay, for regression, it happens to be the ds. Anyways, I mean, this is not very crucial, but we may come back to it later. Any questions about this? I want to rederive this criteria. Basically, there's roughly one criteria that comes out of these different methods, except for the BAC. I want to derive it differently, more directly. You see that the same thing comes out if you do it differently. So we saw that the risk was this, BS plus sigma squared ds. This is unseen. And we saw that this guy, SSE of S, is not a good measure. So what I can do is actually calculate the expectation of it and then try to correct directly via that formula. So let's calculate the expectation of SSE. So you see the same thing comes out more directly. So if I look at the SSE, it's just the expectation of, um, what is it? It's like y minus mu hat, right? If you want, yeah. Sorry? Yes. So, and this is like HSY. So I get expectation of I minus HS times Y squared, right? And then I'm going to plug in what is this? So this is what, mu plus epsilon. And then I'm going to expand. So you get expectation of norm I minus HS mu squared plus norm I minus HS epsilon squared plus 2 I minus HS mu. Do I want to write down? So there is a cross there. We can write it down or not. So you get basically one term is this. The other term is this. So you get transpose of this times the other, and then you can use maybe if you want. It doesn't matter because it's going to be 0. So it's going to be like something like this if you want. Using idempotence, it would be something like this. So past expectation, this thing is going to be 0. Expectation of it is 0. And the expectation of this quantity is very similar to what we did. We did it in a couple of slides. So the expectation of HS epsilon squared was sigma squared times the trace of HS. So this thing is going to be, so the first term is constant, comes out. The second term would be sigma squared times the trace of I minus HS. Okay, very similar to what we just did. And this is n minus ds rather than ds. Okay, and this is really the bias term that we had. So what we end up having is really the bias plus sigma squared n minus ds rather than sigma squared ds. And you can see the problem here as well. If I try to increase the number of predictors, the bias generally goes down, and this term also goes down because it's negative ds. So it's like favors larger models. Okay, but I can now do a very simple correction. So I know that this has the correct, like the bias is in there, and this part is the problem. So I subtract this and add back this, and I get the prediction error. So what I can do here is we can correct SSE by removing sigma squared n minus ds and adding sigma squared ds. So what happens is that I get SSE of S minus sigma squared n minus ds plus sigma squared ds, which gives me SSE. If you compute it, it would be negative n sigma squared plus 2 sigma squared ds. Okay, so you're seeing the same quantity here that appears. This is constant, doesn't matter when you try to minimize over S. So this quantity is going to be unbiased. So the expectation of this would be the same as the risk, the way that we calculated it. So you can see once I remove this and add back the correcting, the expectation of this would be, so whatever this criteria is, the expectation is going to be the risk. Just give me maybe 2 minutes. So that quantity is unbiased, for this quantity is unbiased. And if I drop this, you can see this is just exactly the same thing that we had before. So that extra term doesn't matter for model selections. But if you divide by sigma squared, you get this criteria, which is unbiased for I mean, this criteria, yeah, let's not do this. If I divide by sigma squared and actually plug in sigma squared hat, or it could be SS squared, this gives me a criteria which people call Mallow's CP. Okay, like a very classical criteria. It's just basically equivalent to this unbiased estimator of the risk if you knew sigma squared. If you don't, it's like a little bit of a caveat. But the thing is that this CP you can actually calculate, and for adequate models, it would the expectation would be close to ds. The approximation is because this is approximate. If this was sigma squared, for adequate models, the expectation would be exactly ds because the bias would go away. And we know that this CP is unbiased for, let's call this CP tilde S. If I divide it by actual S sigma squared, the expectation of CP tilde would be really equal to R mu S divided by sigma squared, which would be ds divided by sigma squared plus ds. So when there's no bias, it would be equal to ds. So for adequate models, on average, you would see that these are equal like to ds. But once the model is underfitting, then there is a huge bias. Usually this jumps up. Okay, so you can, by minimizing the CP, or traditionally they look at the models, they plot the models, the adequate models are close to the 45 degrees. So if you have like, the model has ds parameters, the CP, if it's close to ds, then the model is adequate. If it's like above this line, it's not adequate. And then as you go up, the good models are near the line, but you don't want to, I mean, it's going to increase because um, the line increases or ds increases. You can see like the one that minimizes it would be the first model that's adequate enough and also would be close to the line. Anyways, it doesn't matter exactly what this is just the same criteria as the same idea. Okay, it's just add this extra thing here, which really doesn't matter um, for model selection. If you minimize based on CP, it's the same. I mean, if you knew the sigma, it's the same as if you minimize based on the optimism. It's the same criteria as this, for example. Okay. Okay, I think we're out of time, so I'm going to stop here and come back next time, talk about two more criteria and a little bit about consolidation, and then move on. Okay, thank you.